go to that. Okay, so this works. Okay, right. So it's a pleasure to have Sarah with us. In quotation marks, Sarah got a master's degree in physics in Berlin, and then a PhD also from the Technical University of Berlin on non-Markovian processes far from equilibrium. And she's then been a postdoc, among others, in Leipzig, in Germany, then at ICTP in Trieste, until very, very recently. And just a few days ago, or I don't know, or a few days ago,
last week,
she moved to Cambridge, UK, to the Department of Applied Mathematics and Theoretical Physics, or DAMT. And that's where she's now. And the title for the talk is The Role of Non-Conservative Interactions in Non-Equilibrium Systems. So it's a pleasure to have you here. The screen is yours.
Yeah, thank you, Tobias, for the nice introduction, and also, of course, for the invitation. So it's a great pleasure for me to tell you a bit about this work that I've been doing on non-conservative interactions. And you already named all the institutions, and according to this list of institutions, this is also my list of co-authors and collaborators. So in particular, Edgar Roldan, who was my supervisor at ICTP, and Sabine Klapp, who was my supervisor at TU Berlin, and Klaus Kroll, who was my supervisor at Leipzig University. So I want to start with setting the broader scope or the general topic. Yeah, so recently there's a lot of interest in applying ideas from statistical physics to systems that operate very far from equilibrium, such as biophysical systems or active matter models. So here I put some examples: swimming of bacteria, a cellular sensor, a hair bundle, which is a cell in the ear, or here the swarming of fish. And it's a great goal to find theoretical description from the perspective of theoretical physics of these systems. And in order to do that, we have to unravel what are the fundamental principles that govern these systems, what are universal mechanisms, and what are suitable order parameters, and so on. And one way of looking at them is, which is very fashionable in the past years, is to look at them from the perspective of statistical mechanics, in particular identifying non-equilibrium phase transitions. So for example, a swarm of fish undergoes a non-equilibrium phase transition if the density is increased. And another way of looking at them is from the perspective of stochastic thermodynamics. And this is a theory which is quite recent, and it generalizes the concepts from thermodynamics to systems far from equilibrium, and also to systems that are subject to strong noise. And I think this is quite intriguing, because after all, we know that thermodynamic laws are sort of universally valid. So for example, the second law of thermodynamics applies to all kinds of systems and on all scales. So it's quite intriguing to think about a theory that can really capture more than that for non-equilibrium systems. Yeah, and as I said, these theories are now applied to biological systems, active matter, robotic systems, and so on. And these are, however, of course, not the kind of systems that these theories were originally designed for. And if we apply these theories, we have to acknowledge that in these models, usually all variables that emerge are coarse-grained, effective variables, and that also means that the connection to first principles is often very elusive, or maybe sometimes it's even lost completely. And for that reason, yeah, conservation laws and symmetries that we know from classical statistical physics or traditional thermodynamics do not have to hold, and we cannot rely on first principles. So this is, of course, a very, very big and general problem. Let me give an example. So first of all, of course, also the kind of passive systems that have been traditionally considered in, for example, traditional thermodynamics can be out of equilibrium. However, in this case, usually the system is brought off equilibrium via the system boundaries or the initial conditions. So of course, if we think of a Carnot cycle and we compress a gas, this is also a non-equilibrium situation. but the system will eventually relax to equilibrium, and the energy input only comes from the system boundaries. And this is in sharp contrast to non-equilibrium systems, which do not have an equilibrium state. And in particular, here, the energy comes correlated with the stochastic particle dynamics. So for example, a fish in a swarm has a self-propulsion, and this means that there's energy inputted into the system on the level of the stochastic trajectories. So this is very different. However, if we look closely at a swarm of fish and we consider these fish as particles, they of course have many more differences to a molecule in a gas. For example, these are cognitive agents. They have the ability to process information, they can have memory, and so on and so forth. And the interactions between two particles, or fish, is typically a non-conservative interaction. And this is the topic of the talk today. So this energy input on the level of the individual particle trajectories, which is very well acknowledged in the field of active matter. And this is kind of a very big paradigm. However, the fact that also interactions can be non-conservative has not been considered so far. But I think it's very interesting, and it's something we have to acknowledge. So let me give you two examples. Why are interactions non-conservative? So first of all, what does it mean? It means that the interactions are not, you cannot represent them by an interaction Hamiltonian. So they are not the derivative of an Hamiltonian. And one example is, for example, the presence of time delay. So if we consider the blue and the red fish, they will not interact with each other instantaneous as the two atoms in the gas do, but there will be some finite information processing and signal travel times, which means that each fish only reacts to the past of the position of the other fish. And these time delays are known for biological systems, some biological systems, and it is known that they are often on a timescale that is comparable to other dynamical timescales, so we should not neglect them. The other thing is that the interactions do not have to be reciprocal as conservative interactions. For example, the red fish will react to the motion of the blue fish, but the blue fish might not respond to the red fish simply because the blue fish doesn't see the red fish. And this gives rise to a kind of interaction where the two interaction terms don't sum to zero because the Newton's third law, act 0 equals react 0, is broken. And yeah, if you look closely onto the time delayed interactions, you might notice that time delayed interactions are also a special case of non-reciprocal interactions. Yeah, so these are two ways how non-conservative interactions can appear, but there are also many examples on the micro scale. I just wanted to choose something which is very easy to see. Now, having non-conservative interactions brings the system also out of equilibrium, and it does so in a way that is a sort of higher order drive, because this is now a non-conservative term that is not only on the level of an individual particle trajectory or the dynamics of one particle, but it is correlated with a pair of particles. So in a sense, it's a higher order kind of activity. And I think this is quite interesting because that means we have a drive which is directly correlated with structures that are forming rather than individual particle trajectories. Yeah, and this motivates me to look at the question, what are the thermodynamic implications of having such non-conservative interactions in our system? Now, for the remainder of the talk, I want to first give you a little bit of framework of stochastic thermodynamics that we want to use to study non-conservative interactions. Then I will give examples for local effects of non-conservative interactions. So by just looking at one or two particles, first delay and then non-reciprocity. And then I want to give an outlook on the global effects of non-conservative interactions on collective dynamics. First, a non-reciprocal XY model, and second, a VCheck model with time-delayed interactions. And if you have any questions, I'm very happy if you just interrupt me and let me know if something is not clear. Okay, so first, I want to introduce briefly a quantity that is very central in stochastic thermodynamics, and that is the stochastic entropy production, which can in principle be defined for any dynamical quantity, x. So assume x is some dynamical quantity, which typically is subject to noise in the systems that we want to consider. And x denotes a trajectory. I don't know if you can see my cursor. I hope you can see my cursor. So,
yes, we can.
Okay, perfect. Yeah, so let's say x is a dynamical quantity and it performs a trajectory over time. Now, the stochastic entropy production along that single fluctuating trajectory can be computed by considering the logarithm of the ratio of the path probability to see that very trajectory divided by the path probability to see the backwards image of that trajectory. And I think this is quite nice because this literally measures the time reversal symmetry breaking of the dynamics. And indeed, it gives us the thermodynamic error of time. And automatically, on average, this fulfills the second law of thermodynamics. So it's always non-negative. And if this expression is on average 0, this is an indication that our system is in thermal equilibrium. And what is nice about this definition is that in principle, it can be applied to all scales. It has recently been, for example, generalized to field theories. It's to a certain extent model independence, and it can also be measured in experiments, which has recently been done in these works on biophysical systems. And what is really appealing from a theoretical point of view is that there is a connection to energetics by the framework of stochastic thermodynamics, which I will introduce now. So suppose you have a system that you can describe by a Langevin equation. This also works for other descriptions like master equations, but I just want to give this as an example, where we would typically have a friction and a noise term, and some external forces may act on the system. And in this talk, I will consider White's additive Gaussian noise. Now, if we apply this definition to this Langevin equation, we will find that the entropy production along an individual trajectory is composed of two terms. First, the change of system entropy. And the other thing is the medium entropy change, which is given by the heat over the temperature. And the heat can also be quantified directly from the Langevin equation and is given by the friction times displacement minus the noise times displacement. So I think this is also quite intuitive. Friction passes energy from the system to the surrounding bath, and noise passes energy from the bath to the system. So in the steady state, now this system entropy term is usually is conserved. So the only contribution is the medium entropy. And from the second law of thermodynamics, we thus know that the heat dissipation is positive. So a nice example system is just a colloidal particle in a heat bath. And this second law tells us if we steer the particle from outside, the effect will be that we heat up the surrounding. If we apply this to two systems that are in two heat baths at different temperatures that are coupled with each other, it will tell us that the heat is always extracted from the hot bath and passed to the cold bath. So the cold bath will get warmer over time and the hot bath will get colder. So this is quite clear, quite intuitive, and this is just a generalization of these ideas from thermodynamics to the micro or mesoscale. However, there are some assumptions hidden in this framework. One is Markovianity, and the other one is that all interactions that appear are conservative. And we want to see what happens if these are violated. So first, let's look at time delay. So time delay can occur also on the micro scale due to viscoelastic properties, hydrodynamics, chemotaxis, or feedback, or something like this. And we want to study what is the effect of having time delay. In order to study that, we look at the most simple equation that we could think of is a one-dimensional Langevin equation, one variable Langevin equation with a potential term, a noise, friction, and this force that is non-local in time, which is a time delay force. So here we have a convolution with a memory kernel. And for this memory kernel, there are different functions are very convenient to use. So these were the ones that we consider. First, a single delay, where this memory kernel would just be a delta peak around a single delay time. And in this case, this equation simplifies to a stochastic delay differential equation, which is known to be infinite dimensional. There is no closed Fokker-Planck equation. And it's known that the delay can induce oscillations or chaos, even in the first order delay differential equations. And only for linear systems, this equation has been solved. And from that, we know that the system settles in a non-equilibrium steady state with a Gaussian probability density. Another very common model is gamma distributed delay. So here's some plots of this. So for here we have this parameter n, and if n is 1, this is an exponentially decaying memory kernel. If n equals 2, we have a peak, which gets more pronounced if we increase n. And this way we can model different memory kernels that have different shapes. And this is a model that is very convenient because it obeys a Markovian embedding. So instead of looking at the Langevin equation with delay, we can look at Langevin equation with more variables that doesn't have delay, which is shown here. And the first variable of the set of equations has exactly the same dynamics as the Langevin equation. So this is why these gamma distributions are quite convenient. And that's also the way we used in order to address these questions. So I don't want to go into a lot of details. I just want to show you some results. So this were was a bit of the technical background. Now, if we apply this entry production to a system with time delay, let's say this Langevin equation here. So we have just a time delayed force here, and the rest is as before. We should compare the probability of a forward motion with a backward motion. Now, if we have time delay, this backward process becomes a very peculiar object. Namely, if we have a history dependency and we reverse time, this turns into dependency on the own future. So this is a stochastic process that depends on its own future. And this is acausal, and it's quite strange object. And it turns out that dealing with these path probabilities is very complicated. And I think physically the main message that we can take out of this is that having a time delay introduces a different kind of error of time. And this is because we can always only memorize our past, but we cannot memorize our future. So if we apply this definition, we find that in addition to the heat and the system entropy change, there's now an information theoretical contribution that comes from this acausality. If we look at the heat dissipation, we find this is given by the same expression, so we can calculate it. And what we find here is that the heat flow can have a different sign as in a Markovian system. So by steering a particle from outside with the delay force, we can actually cool down the environment and extract energy from it. And this can happen for small and intermediate delay times, so you don't even need a very long delay. And it happens in linear and nonlinear systems. It happens for single and also for distributed delay. So it's a quite robust result. And if you now ask yourself, how is this possible thermodynamically? We steer from outside and thereby cool down a bath. We should acknowledge that this drive doesn't come out of the blue, but it comes from some external feedback controller. And this controller might also dissipate heat so that overall the second law of thermodynamics still holds. This is what I wanted to say in a summary about this delay problem. Now I want to turn to non-reciprocity. In order to study what non-reciprocal interactions do to a system, we consider the most simple example system, which would be a linear system of n degrees of freedom. And in this case, the non-reciprocity just means that the coupling matrix between the different degrees of freedom is asymmetric. And here I show it for 2 particles, but since this is a linear system, we can solve this analytically also for arbitrary system sizes. And yeah, so the non-reciprocity just means that these off-diagonal elements have different entries. And you can think of x1 and x2 as the position of 2 particles in 2 different heat baths, if you like. And oh, sorry, this should be A12 and A21. So if the off-diagonal elements have the same value, this system reduces to a system, to a mechanical system. So this model could represent a mechanical system like 2 springs coupled by 2 beads coupled by a spring. And if not, this is non-reciprocal. And I want to give you an example for the dynamics. So if the off-diagonal elements have different signs, we can have a run and catch scenario. So one particle is attracted to the other one while the reverse interaction is repulsive. And that would yield a situation where these 2 particles would like chase each other. And yeah, now for the general case, we considered a lot of thermodynamic properties like detailed balance and heat dissipation, entropy production rate, and so on. And what we can show is that generally the system settles in a non-equilibrium steady state where it dissipates energy and detailed balance is broken. However, there are some exceptions. If we also introduce a temperature gradient, so T1 and T2 have different values, then we can recover a pseudo-equilibrium situation where everything balances out and the system looks like an equilibrium system. It doesn't have dissipation, there's no irreversibility. So the 2 drives, having a non-reciprocal coupling and having a temperature gradient, can compensate each other. However, if the non-reciprocal coupling is even stronger than the temperature gradient, we can also pump energy against the temperature gradient. So in this case, we can find situations where heat is extracted from the cold bath and deposited into the hot bath, different from the direction that you would usually always have in a thermodynamic system. Of course, overall, the second law of thermodynamics holds. So if I sum the heat flows together, we still dissipate energy on average and produce entropy in particular. In order to see better if these results really hold in an actual system and are not somehow an artifact of our description, we realize this now in a molecular dynamics simulation where the baths are not just given by friction and noise terms, but are really resolved. And we have here argon fluids, and the particles are 2 nanoparticles. And we, from outside, impose these non-reciprocal coupling, and we studied the heat flow, and we found that indeed we can find conditions where the direction of heat flow is reversed. So the cold bath gets even cooler and the hot bath heats up over time. And then using the framework of stochastic thermodynamics, we can also access things like the distribution of work and heat. And there are universal bounds that bound these distributions. I don't want to go into the details. I just wanted to mention that there are many more things that we can do with this framework. And we also have considered the efficiency in the system. So if I want, I can consider this like a refrigerator. I can say, I provide a non-reciprocal coupling, which costs me some energy. But on the other hand, I can pump energy against the gradient and cool down my bath. So let's look at this like a refrigerator. So in this case, the efficiency would be given by how much heat we extract from the cold bath, divided by how much energy we have to provide. And here we find that the fluctuations of this efficiency obey a power law. So you can be at short times almost arbitrarily efficient, but also very inefficient. And this was just to give you a glimpse of what one can do with the framework of stochastic thermodynamics. A question which is very relevant in this context is what happens if only partial number of degrees of freedom is observable or even physically meaningful. And indeed, in many models where these biophysical models, one degree of freedom is an actual degree of freedom that can be measured, and another one is just an auxiliary degree of freedom. So what happens to the observations that we made, and how can we, what do we do in this case? So for example, if one degree of freedom is just an auxiliary variable, what happens to the heat dissipation? What happens to the second law? And what we found is that in this case, we can generalize the second law by introducing information flows. And in particular, in this case, the heat dissipation of the remaining degree of freedom would not be bounded from below by 0, but by the information flux between the degrees of freedom. And this is a situation that is well known from the thermodynamics of feedback systems. So whenever you have multiple non-equilibrium degrees of freedom that are coupled, and you want to coarse grain some of them and want to look at the remaining entropy and the remaining heat dissipation and so on, you have to take into account the information flows between the degrees of freedom that you keep and the ones that you have coarse grained out in order to connect dissipation and entropy production and so on. So here we just showed that this class of non-reciprocal systems falls into this category of feedback systems and can also be considered from that perspective. Okay, so this is what I wanted to say about the situation of just having 1 or 2 degrees of freedom. And now in the remainder of the talk, I want to discuss a little bit many-body systems. So we wanted to understand the impact of having non-conservative interactions on collective behavior. And in order to approach this big question, we consider an example system. And here we considered XY model with non-reciprocal coupling. So this is a 2-dimensional XY model, which we realized on a hexagonal and on a square lattice. And we consider the question which phases emerge in the presence of vision cone interactions. So the modification to the standard XY model is that we exclude the neighbors in the interaction term that lie behind a spin. So in this case, for example, the green spin would be coupled to the purple spin, but the purple spin would not be coupled to the green spin. And that means that in the interaction Hamiltonian, we modify the interaction term by just setting some of the coupling terms to 0, those that are lying behind the spin. Yeah, so this is a non-reciprocal version of an XY model. And theta represents the vision cone of the spins. And if you like, this also represents a 0 motility limit of an active system. So if you think about flocking system or so on, and you would go to the 0 motility limit, it would look very similar to an XY model. And so if you like, you can also think about it like this. So it's like a flock of birds in the co-moving frame. Yeah, and the most striking finding of this from our, so we performed Monte Carlo simulations to solve it. And the most striking finding is that in addition to the disordered phase and the quasi-long range ordered phase, we find a long range ordered phase emerging in the case that the vision cone is smaller than 360 degrees. And interestingly, it doesn't really have to be very small. So even if the vision cone is almost 360 degrees, you can find long range order. And in the usual XY model, this would be permitted by the Mermin-Wagner theorem. So the non-reciprocity can introduce long range order in 2-dimensional systems with continuous spin symmetry. And yeah, so we have an archive article on the system that came out today. So if you're interested, please have a look. The nice thing of this model is that because it's quite simple, we can rationalize a lot of our findings by using arguments well known from equilibrium statistical mechanics. So for example, below 60 degrees, in this case, no quasi-long range order appears. And this is because here the percolation threshold is hit. If we have less than 60 degrees, we can only see one neighbor. So the best we can do is to arrange the spins in this way. But then we only we don't have bond percolation. So their individual sublattices are formed that are not joined with each other. So this is explains the absence of quasi-long range or long-range ordered phase in this regime. Then the emergence of long-range ordered phase can also be explained by an argument well known from equilibrium statistical mechanics. And that is the fact that long wavelength spin waves that usually destroy the order in two-dimensional XY models are suppressed by division cones. So if you have a classical XY model, what happens is that you can excite a spin wave which has the longest possible wavelength. So it just rotates once over the whole system size. And this spin wave in the thermodynamic limit has zero energy. So you can always excite that more or less for free. And this destroys the rotational order. Now, if you have vision cones and you want to make this turn, you will have to enter some angles where you lose neighbors. So where the number of spins that you see is less than the optimal number. And this is because, you can see that the number of spins at each, for example, here the yellow spin just sees 2 spins while the red spin sees 3 spins. So if I want to make a full turn, some spins have to be in this unfavorable configurations. And that means that the energy to excite this longest wavelength spin wave doesn't go to 0, but it's diverging in the thermodynamic limit. And therefore, the noise cannot excite this mode. So we can understand why we have long range order. However, for vision cones that are multiples of 60 degrees, these spin waves can again be excited by noise, because then you always have a constant number of neighbors. So this is why for 120 and 180 and so on, we don't find the long range ordered phase. So it's quite nice because it's a system very far from equilibrium, but we can still understand its behavior from the perspective of classical statistical mechanics. A very striking feature is if we look at how defects propagate in the system. So in order to visualize that, we have prepared the system in the long range ordered configuration. And at time 0, we rotate the spins in the middle and thereby introduce 2 defect lines at the interfaces between here the yellow and the red regime. And if we start the simulation, we see the following. So these defect lines propagate in a directional manner. And this is, of course, very different from the way that defects would propagate in an equilibrium system. And in particular, this breaks the parity of the system, but it also breaks the time reversal symmetry. If we would play this video backwards, the defects will propagate in the wrong direction. And we can measure this by the entry production rate in the way that it's the same definition now, just applied to the spin system. And here we find a pronounced maximum that lies here, right in the disordered phase, close to the transition to the quasi-long range ordered state phase. Yeah, and lastly, I think coming to the end. Lastly, I just want to say that we also realized a collective system with time-delayed interactions. And here we consider the VTEC model, in which case we have spins which travel in the direction that they point to, and they interact in the following way. So at each time, each spin scans its local environment in radius r, and then it flips to the average orientation within this radius. And now, as compared to the standard VTEC model, we have introduced a delay time. So the flipping of the orientation occurs with a certain delay time. And what we found is that having time delay in the system actually stabilizes the formation of swarms. So an intermediate delay is beneficial to find order in the system, while large delays counteract ordering and make it harder for the system to order. Yes. And with this, I want to come to an end. So I hope I could show you some, give you some insights that non-conservative interactions are very important. They can introduce a rich thermodynamic behavior. In particular, we found these anomalous heat flows from cold to hot. And if we consider collective behavior, long-range order can be introduced. And we also find this directional defect motion. And of course, there are many open questions. One important question is to connect the local stochastic thermodynamic properties that I showed to the global phase behavior. This is completely unclear how these things are related with each other. And then a better understanding of the entropy production rate is also something, a bigger goal. And with this, I want to thank you again for your attention. And of course, I'm very happy to take questions. Also, if there's some things you're more interested about or you didn't understand at all, please just drop me an email and we can have a discussion. And this is a list of the main references where these results are published. So thank you very much.
Thank you for this talk. So this is open for discussion or comments or questions. If anybody has any, just unmute yourself and ask.
Hello, hi Sarah, this is Raul Toral.
Hi.
Thanks for the talk. I have a question concerning you have the definition, the entropy production for a trajectory, okay?
Yes.
As the log of the probabilities of the reverse and the backwards trajectory. And then you extend that definition to a system with delay. So I wasn't sure how to interpret the backwards trajectory in the case of delay. You talk about depending on the future. Can you be a little bit more specific about this point?
Yeah. I was very short about this because I wanted to give an overview over many things. Wait, let me go back to it. But I mean, this is a really big question, how to do that properly. So wait. So there's different approaches to deal with this question. So first of all, I should say that if I look at the system with time delay, the probability to extend into the future doesn't only depend on the instantaneous time, but it depends on the whole interval. So in principle, if I switch the interval, I also get this dependency on the whole future interval. And so if I write the wait, I think I have a backup slide, right? I think it makes it easier to look at that. Okay. So sorry.
Okay.
Yes, so in principle, you would have to also switch this entire interval. And you can also go to a description where you, instead of looking at X being the system state, look at the entire path between time t and t minus tau at the system state, and then consider this problem in the infinite dimensional space. It doesn't make sense to you. So instead of saying I have a dynamical system where X at time t is my system state, and this is non-Markovian, I can also say my system state is X, the whole path between t and t minus tau. And this system state, this is my system state. So then I'm in an infinite dimensional system state. And this has a Markovian evolution. And this is what we did. So then in this infinite dimensional system state, you can just use the usual Markov theory because it has a Markovian evolution. But then if you want to go back to the non-Markovian picture, because you just want to say X at time t is my system state, then you have to cos-grain out these additional degrees of freedom that you get.
So you go from a non-Markovian, which is the time delay, to a Markovian representation by
Yeah, by embedding this
infinite dimensional space. Okay, I can more or less guess how you can do it.
Yeah.
And then when you do the backwards, then you need again to coarse grain the information.
Yes, exactly. So this is one way of doing it. But from that, you can see that it's quite technical, and you get these information theoretical contributions from these additional degrees of freedom. That's why I kept it like very, very abstract on the slide. But
so in the case the delay has this gamma distribution, is that any easier there?
Yeah, in this case, it's easier because in this case, you can embed it in a finite dimensional space. Yes. So you can just have 1 or 2 additional degrees of freedom. Then you can do the same thing. But then again, if you want to go back to the original representation, you have to coarse grain these additional degrees of freedom. And you get, you still have to do that. And this gives these additional terms, which are not classically there if you have a Markovian system.
Okay, thank you.
Thanks for the question.
Any other questions or comments?
Hi, this is Emilio Hernandez. There is a part of thermodynamics where there are many parts of thermodynamics I haven't understood, but one of them is the thermodynamics irreversibility, time reversal, and all that in classical case with magnetic fields. In fact, magnetic fields is one of the interactions in which you typically has, even at the classical level, you have non-reciprocal interactions. So you have two charged particles, and you move one of them, then the force of one on the other does not respect the third law. The force of the other on the one is not reciprocal. My question is, in this apparently simple system, it's not active matter, is there any phenomenology related to the non-reciprocal interactions you have described to us now?
Yeah, I think, the model that I used here is, it's very, very basic, right? So I just have 2 or n degrees of freedom, and the non-reciprocity is just in the sense that my coupling matrix is asymmetric. So I would expect that these systems are also falling into this class. And I also should say that different from the non-Markovian situation, considering the thermodynamics of non-reciprocal systems doesn't have technical issues at all. So you can think of this as a drive, and you can apply the usual thermodynamics. So I'm not so sure about these magnetic systems, but I assume that it's just going to be very similar. And here I also don't have a complicated active matter system in reality, right? I just have linearly coupled degrees of freedom, and probably these magnetic systems are much more complicated. But indeed, the emergence of non-reciprocal interactions can come from many, many different mechanisms. It doesn't have to be something super high level complicated as these vision cones. It can also just be the presence of a flow, for example. If you have particles in a flow, and so colloidal particles in a fluid, in a bath with flow, then also the effective interaction between them would be non-reciprocal. Mm-hmm. Or also in plasmas, hot plasmas, the interactions are usually non-reciprocal. So it doesn't have to be something really very high level complicated as a swimmer. I just use them as examples because there it's quite easy to see where it comes from. Thank you.
Yes, thanks.
Okay, any other comments or questions? Or
I think Gonzalo was saying something, but you were muted.
Yeah.
Or at least I cannot hear you, Gonzalo.
No, we cannot hear you. We cannot hear you.
But hi, by the way. No, I cannot hear you. Oh, maybe you can write it in the...
Yeah, you could write it in the chat and I can read it out if you want, or I don't know what's happening. Let's see. So I don't know if everybody can. Hi, I was just wondering about the relation of delay with feedback control scenarios.
Yes, thank you. yeah, there's a lot of relation between them. So first of all, whenever you have some sort of feedback control, you if you really take everything into account, you automatically have a delay because you have to measure and then you can only apply the control a time later, which you cannot do that instantaneously. So typically there is a delay, and that is, for example, also relevant in all these feedback experiments on colloidal particles that are very fashionable in stochastic thermodynamics and are used to realize many things. So if you look closely, you will always have a delay. And then also from the results that I was showing, I also made this connection to, I also said here that, yeah, there has to be a controller, right? So this is also a way of interpreting the results. But if you want to do the thermodynamics for this scenario, you can do two choices. Either you say, I just want to look at the trajectories of X alone, then I have to deal with the delay. Or I could say I describe the system plus the controller, then I don't have the delay because it's automatically incorporated. It can be a Markovian model. And I would hopefully find the same thermodynamics for the particle. But of course, the description would look very different. But indeed, the emergence of these information theoretical terms are also very common in the feedback description. And it's a very similar framework. But the thing is, one thing that I also want to point out, in many models for control, it is assumed that the controller measures and interacts at discrete times with the system. So there would be a point where it measures, and there would be a point where it interacts with the system. And that is, of course, much easier to describe as a delay force, which sort of measures and acts continuously all the time. And in particular, if you measure and interact at discrete times, you can always chop up the trajectory between these measurement and feedback times where you apply the feedback. And then one of these elements would always be Markovian. So you can describe the whole thermodynamics by just looking at these pieces of trajectories. But here, where we interact with the system all the time, we cannot do this. So we cannot just circumvent this and look at between these two times. So this is why the framework by many the traditional papers in thermodynamics cannot be applied directly, and it's way more messy here. But I think for many realistic systems, there is a continuous interaction, so we cannot always do this probably. Thank you for the question, Gonzalo.
Okay, anybody else? So Gonzalo says thanks a lot in the chat. So any other questions or? So I had one. You said that if the delay is gamma distributed, you can. I understand, right? You can break it down into little pieces, as it were, right?
Yeah.
But can you do that, like for a general distribution? Can you also do this at least in approximation somehow? So basically, can any distribution be written somehow as a sum of exponential distributions with suitable parameters to some?
I think except for scale-free distributions like power laws or so,
right,
then you would need infinitely many to approximate it. But if it's anything else, you can probably always approximate it by a sum or it's not just a sum of exponentials, but it's a sum of exponentials times polynomials, if you look closely.
Times polynomials.
Yeah, so it's because you can couple also the auxiliary variables with each other. And then you can also get these.
I see.
Yeah.
Okay.
But overall, you have something exponentially decaying. And if you would like to have a scale-free power law thing, then you need infinitely many. But if not, I think, you can always approximate it. And also what we found is if we look at things like the heat dissipation or also the stability of the process, often a crude approximation of the memory term gives a quite good approximation of the behavior. So you don't necessarily need all the details in the memory kernel, if you're depending on what you want to achieve, of course. So sometimes it can even be enough to just have two exponentials with the relevant timescales, and then you're good to go. And I think in particular, this discrete delay time is the most complicated one in a sense. And you can approximate that very well by a gamma distribution with 2 or 3 timescales, or like a parameter n equals 3 or something. So it's not really necessary to go to this infinite dimensional case.
Okay, all right, thank you. Anybody else? Any comments or questions for Sarah? No? No, doesn't seem to be the case. Well then, thank you again.
Thank you.
And now, well, there's no other thing we can do other than to close the call. So thank you again. All the best.
Yeah, thanks again a lot for the invitation and for everybody for listening and the questions as well. So yeah, see you.
Okay, bye-bye.
Thank you. Bye.